When you heat or cool an object, you do more than change that object's temperature. One thing that's very common is materials that are heated or cooled can expand or contract. Now, see how heated usually means expand, cooled means contract, but that's not always the case. When you change the temperature of something, you can change its size. The amount of that change depends upon the property of the material. So this is incredibly important in a lot of different ways. For instance, any type of manufacturing, right? When you have a car put together, that car in the winter, those metal pieces might shrink a bit, or in the summer they might expand a bit. You have to make sure that the pieces fit in such a way that that expansion and contraction doesn't wear out pieces of the material, doesn't wear out the joints. A very important thing that, fortunately for us today, has been addressed, fillings. If you have dental fillings, the material they use to fill your teeth, amalgam, has to have the same temperature properties as the enamel of your tooth. Otherwise, when you drink something hot or drink something cold, your tooth changes size slightly, your filling changes size slightly, and if they don't change size by the same amount, that causes basically pressure to build up. For example, say your filling expands faster than your tooth does. In the past, teeth have exploded because of this property. Fortunately for us in modern dentistry, they've actually gotten that under control. Another fun thing is if you have different teeth, different fillings with different chemicals, you can actually have a battery set up in your mouth. Fortunately for us, again, that is not the case anymore. So we have materials that change size. Now, when we talk about solids, one common thing we think of is length. For example, the length of a bridge. The Golden Gate Bridge is a large metal construction that changes temperature. Day-night temperature changes and summer-winter temperature changes can change the length of that bridge. Now, you pick materials, hopefully, that minimize this change. Some materials are more sensitive to temperature changes than others. But at the same time, you also pick cheap manufacturing materials. So you have to, in your design, take in these temperature changes into account. So, for example, a steel beam. A steel beam can actually change length depending on the temperature. The equation for linear expansion, and we call the expansion in one dimension linear expansion. For example, think of the sidewalks that you have outside of your house. They're cut into squares, right? They don't just pour a long section of concrete, but they break the concrete up into squares. So during the hot summer days, that concrete expands a little, those gaps get smaller, and during the winter, the concrete contracts, making those gaps a little bit larger, but it prevents if you just did one long pour, eventually the temperature would cause those cracks to develop. And once you get cracks to develop, you get water in there, you cause expansion. When the water freezes, we'll talk about that in a moment, causing wear and tear of sidewalks. So linear expansion, the change in length of an object depends on its original length, how long is the object at the current temperature. The change in temperature, how much are you changing the temperature? Because if an object changes length with temperature, if you double the temperature change, you might double the length change. And this variable alpha, now we use this for angular acceleration, we're using it for something else now. Alpha is a coefficient of linear expansion. And your book gives a bunch of examples. You can grab a handbook of physics and chemistry from the online or from a chemistry lab, if you're in a chemistry lab, and that will give you values, and we'll actually have a lab, of course, measuring these for common materials. So stainless steel has a different coefficient of linear expansion than copper does, than iron does, than aluminum does, than steel or gold or silver and so on. So you have to measure these in the lab. But when you do measure them in the lab, all gold has the same coefficient of linear expansion for the same type of gold, right? Pure aluminum has the same linear expansion for all other pure aluminum. Different alloys, you have to redo the experiment to see how a mixture of aluminum and nickel, for instance, might have a slightly different coefficient of linear expansion than pure aluminum does. So you can measure, usually the temperature will increase. The length will increase as the temperature increases. There's usually a positive correlation between those two. Now, that's just for solids, one-dimensional. Liquids don't have that length expansion because liquids expand in 3 dimensions. Solids do as well, but usually you're only interested in looking at one dimension, like with sidewalks. So we look at volume expansion. So if you have a 3-dimensional object, that object will definitely expand in 3 directions, right? It expands in length, expands in width, and expands in height. So the change in volume an object experiences is equal to the initial volume of that object times the change in temperature again, times this coefficient beta. Beta is the coefficient of volume expansion. And again, you have to look it up. You have to look it up in a handbook of chemistry or physics or in your textbook to get that value. So this volume expansion works for liquids and solids. Linear expansion is just for solids. And for solids, there's a relationship, right? Alpha and beta for a given material are connected. Beta is usually almost always 3 times alpha. So look on your table in your textbook of alphas and betas, you will see that beta is 3 times the previous column. And that's just because objects are in 3 dimensions, right? If you have a steel rod, it's definitely going to increase in length, but it's also increased linearly in this direction. It's also going to increase linearly in this direction. That is 3 times, length, width, and height. That's 3 times the original coefficient. Now, there are a couple of notable exceptions to this. One notable exception is water, and your book talks about water. Water actually does, as you cool, say, room temperature water, as you put it in the freezer and cool it down, its density increases because its volume decreases, right? The volume does shrink as you cool it down to 4 degrees Celsius. At 4 degrees Celsius, water is actually its densest. As it cools further to 0 degrees Celsius, or as water is freezing from 4 degrees Celsius to 0 degrees Celsius, it actually expands again. And water ice, the solid, is actually less dense than water at 4 degrees Celsius. Now that's incredibly important for so many different reasons. You and I wouldn't be here if that didn't occur. Life wouldn't have developed in the oceans had that not occurred. Because that means our oceans, icebergs, float on top, right? Ice floats in a glass. It doesn't sink to the bottom. Almost every other material, if you have a solid of that material and you drop it in a liquid of that material, it will sink to the bottom. The solid will sink. Take molten iron, just above the melting point of iron, and drop in a big iron chunk, that iron chunk will sink. So, why is water special? Well, water, it's a little complicated. Maybe you even discussed this in chemistry class, but it has to do with the fact that the water is starting to form its molecular bonds to form a solid, and those molecular spacings are a little bit further apart, causing the ice to be a little less dense. But it's incredibly important. Fish survive, and think about when a river freezes over, a lake freezes over, the fish can survive in the water underneath that ice cap. Right? The entire lake doesn't freeze over unless it's an incredibly small, like a pond or something like that. There's still water there for the fish to survive. So fish wouldn't survive if the oceans froze solid, if lakes froze solid, which they would if water was strictly behaved with this equation. So water is a neat example. There are a few handful of others, but for the most part, the examples you'll be given are examples where these conditions hold. So you'll be asked to look for length changes and volume changes of various solids and liquids. For given temperature changes, you'll need to look up these values or solve for those values in the problems given.